AP students, this video will begin us thinking about the van der Waals equation. Real gases. They are what we're surrounded with. They are what we collect and produce in lab. But we've talked about that the majority of our laws apply to ideal gases, pretend gases. Well, there's a modification to the ideal gas law to make it apply to real gases, and that's the van der Waals equation. As far as the van der Waals equation, you need to understand it conceptually. I know in the unit assignment, I assigned us a problem, and it is good for us to problem solve with the van der Waals equation. However, we as AP students need to understand why and how the modifications are made to the ideal gas law. All right, so remember that we said the main parts of the kinetic theory of gases that real gases violate, mainly number one, is they do have particle attraction, and then they do have particle volume. All right, now we can rest assured because often ideal gases and real gases do really behave the same. For example, remember we talked about, of course, Boyle's law. If amount and temperature are constant, it's an inverse relationship of pressure and volume. Well, this blue line is showing us an ideal gas, and the green is a real gas. And we can, of course, see that the general shape is the same. And there's definitely portions of this, especially low pressure, where the lines are very close. But as we get to high pressure situations, they get further apart. Also, here's another that, if we would graph PV versus P, an ideal gas should just be a non-sloped line. Well, if we take a look, the greater the particle attraction, the more we deviate from what we would expect an ideal gas to do. So helium and hydrogen, are very lower particle attraction. They're not going to show near what CH4, and that of course is because of increased lung dispersion compared to these guys. Carbon monoxide being a polar molecule. So we do deviate. Along came Johann von der Waals, and I believe he was just fed up with, okay, PV equals nRT, especially at high pressures. Real gases don't obey this. If I take their pressure times their volume, it will not equal moles times this constant times temperature. So what we have is the van der Waals equation. All right, now I'm just going to rewrite because I think on our packet, I want to make sure that we see clearly the math that we're asked. And so instead of just pressure times volume, we have these correction factors, and each correction factor adjusts for the main violations. So if you see, we are making an adjustment to the pressure that we would measure about our gas. So this is the observed pressure. Well, we need to add to that. Well, why? Well, this makes up for the particle attraction that gases have for each other. We know that as a gas is behaving, that it's colliding with the walls of the container and itself, and a measure of that is pressure. Well, they attract each other. So this pulls on this, and this pulls right back. So because of the pull, When this particle strikes the edge of the container, it's not going to collide with as much force. So what we observe is lower because of the attraction of the particles. If they didn't attract, they would be hitting much more strongly. So the particle attraction actually lowers what we measure. Now, we know N is moles, so it depends on the factor, how many we have, that's going to impact the attraction and the holding back. How much space are they moving in, but also this factor A. Now, A and this letter B are dependent upon the material. You would be given these values. So if we look at these A values and just observe, which ones have relatively high A values? We have Cl2, we have H2O, NH3, and then what are the really small ones? Well, these are either polar molecules or they have pretty high Lund dispersion forces compared to these. So these have high intermolecular forces, so they're showing more particle attraction. They're holding back more of each other, so they're not colliding as forcefully. And so we need to add a greater factor. So the greater the particle attraction, the greater the value of A, which then will add a greater value to the observed pressure. So we make this correction to pressure because what we measure is actually lower because of particle attraction. All right. Well, why the correction to volume? Well, remember, this is the observed, the measured volume. This is the volume of the container. Now, we ignore particle volume because we say, there's so much empty space in a gas that really we can negate the actual volume of the particles. Well, when we're at low pressure, probably if we would collect all of these, probably the volume of the actual particles would just be this compared to the volume of the container. So not a big deal. However, if we're at higher pressure, so that would mean this amount, if we just change volume, would be in this. And so do you see how particle volume makes a bigger impact the greater the pressure? So if this is the volume of the container, we need to account for the particle volume. N is moles, B is per your substance. The value of this is based on the volume of the substance. And so, for example, we know helium would be larger than, small, Well, really, these are about the same. Let me see. Oh, like we definitely know Cl2 is larger. Oh gosh, hydrogen, much smaller, and so on. So relative assignment based upon the volume of the particle. Okay, so this adjusts for particle volume of your gas, and this for particle attraction. So this is particularly applicable at high pressures where we see a great deviation of real gases from being ideal, and whenever our gas does have high particle attraction, for example, water in the vapor state. Okay, so we need to understand this conceptually. There are examples in your textbook that show the working out of the van der Waals equation, and you're of course asked to do that in one of the unit assignment questions, but we need to understand this beautiful creation conceptually.